Suppose that 65% of high school students eat breakfast before going to school. A random sample of 500 students were surveyed. We're going to let X equal the number of high school students in a random sample of size 500 who eat breakfast before going to school. Explain why X can be modeled by a binomial distribution, even though the sample was selected without replacement. Why would I be allowed to model this with a binomial distribution, even though they did not replace? What were the things that we wrote down at the top? What were the things that we wrote down? I've got them up there in like a yellowish and a red color. What were their names? The two things that I had you guys write down at the beginning of the class. 10% condition and large counts condition. So when I'm checking for a binomial distribution, I want to check 4 things. We had that acronym BINS. What was the B for? Binary. Kind of like a yes, no, success, fail. What would the success and the fail be on this? Yep, success if they eat breakfast, because that's the thing that we're interested in. Failure is they don't eat breakfast, so it's binary. What does the I stand for? Independent. Whether or not I ate breakfast, independent of whether or not you ate breakfast before you came to school. Yeah. What I chose to do at home and you don't know what I'm doing has no effect on what you're doing. So these are independent things. So it is independent. We have binary, we have independent. What is the N? Number of trials. What's our number of trials? 500. What about probability of success? 65%. So the independent is the thing that we're working with here when we have no replacement. So is whether or not I eat breakfast independent of you, yes, but if I'm looking at a sample of 500 students, the probability when I start removing people isn't technically independent anymore because my denominator keeps changing, right? But do you guys remember before break when we were talking about the big bucket of Skittles? Does my fraction of 2,000 over 10,000 change substantially when I take out one Skittle? 1,999 over 9,999 is almost exactly the same as 2,000 over 10,000, right? So that's where this 10% condition comes in. If the number that I am sampling, in this case, it's how much? 500. If the number that I'm sampling is less than 10% of the whole population, what's the population they're looking at here? Who are we interested in? High school students. Do you think there's at least 5,000 high school students in the world? So if we sample 500 of them, are we sampling less than 10% of the entire population? Yeah, I can get 500 high school students a couple times over just here at Pike. We can get more than 5,000 high school students just like staying inside Indianapolis. So we definitely meet this 10% condition here. So explaining why X can be modeled by a binomial distribution, even though the sample was selected without replacement, because it meets our 10% condition. We still have to show that it's binary. We still have to show our number of trials, 500. We still need to know our probability of success each time, 65%. We're going to go ahead and say it's basically independent because we're taking less than 10% of the population, even though we're not replacing it. Does that make sense? So using a binomial distribution to estimate the probability that 300 or fewer high school students in the sample eat breakfast before going to school. How would I put this one into my calculator? Binomial CDF, is it 300 or less? If I want exactly 300, then I want the PDF. CDF for cumulative. Binomial CDF. The next thing you want into your calculator is N. How many trials? What was that on this one? 500. Then I want the probability of success after a comma. 0.65. And finally, I want the X value that I'm interested in, which is how much here? On number 2, what's the value that we're interested in? 300 or less. I'm going to put 300. Yep. So normally we call our success probability P, but if you call it S, that's totally fine. But you want number of trials first, comma, probability of success, comma, your X value, the value that you're interested in asking about. What do you guys get? 0.0113. Yes. Last one up here, and then I'll pop my answers up. Justify why X can be approximated by a normal distribution. I'm going to head back here for that. Why can we approximate X with a normal distribution? Yes. Expected number of successes. So N times P, that's a number that's bigger than 10. Expected number of failures. So N times 1 minus P is also bigger than 10. If those conditions are satisfied, then I can use a normal approximation for my binomial here. That is what we call our large counts condition. I got 325 and 175. Definitely meet those conditions. As long as we are bigger than 10, my normal approximation is going to be close enough. Nope, number 3, your large counts condition is just N times P, so your mean. And then N times 1 minus P. So this is your mean for your successes, your expected number of successes. We expect to have more than 10 successes. We also expect in our sample to have more than 10 failures. As long as I expect to have more than 10 successes and more than 10 failures, we can use that normal approximation. Geometric CDF. So binomial CDF. This is, I want to know that 300 or fewer. If I'm talking geometric, then I want to know what's the probability that I go through 300 people before I find my first success. So geometric is I'm going to go until I have a success and then I'm going to stop. Binomial is just how many successes am I going to get? Does that help? Yeah. So if you see until the first success, that is geometric. How would I do number 4 here? I basically want to calculate the same thing I was doing in number 2, but I want to use a normal distribution. How do I do that one? We need our mean, we need our standard deviation. How do I find the mean? N times P, so that's my expected value. What did we say our expected value was? 325, that's my mean right there. How do we find the standard deviation? Yes. So we take number of trials times the probability of success times the probability of failure, and then we square root all of that. So we need to find those two pieces. We've got this one. Go ahead and calculate the standard deviation. Square root of n times p times 1 minus p. Tell me what you get. Square root of n times p times 1 minus p comes out to be about Let me grab my calculator and make sure I didn't calculate it incorrectly. I'm gonna have 500 times 0.65 times 0.35. I'm gonna take the square root of 113.75. I got like 10.665. Okay. So I have my mean, I have my standard deviation of 10.665. If I'm gonna do a normal distribution, what do I have to draw? Have to draw your normal curve. You're gonna draw your normal curve, you're gonna label it n parentheses, and what numbers have to go in the parentheses? Mean and standard deviation, so 325, comma, 10.665, have to draw. Right in the center of your bell curve, what do you have to have labeled? Have to have your mean labeled. What do we say the mean was again? 325. So ballpark where 300 would be on there, and then shade everything to the left, because we want 300 or fewer, 300 or less. You got 325 on there, ballpark where 300 is going to be. And then we're going to pop it into the calculator. So as long as you have 300 somewhere off to the left, it really doesn't matter where to the left of the mean, so long as you have it to the left of the mean. Technically, we're going to be more than 2 standard deviations away, so it's just going to be this little tail over here. If you had it a little bit further over, but you have your mean and your standard deviation here, you have your mean labeled, and you have 300 on there and shaded to the left. Let's just scroll down a little bit here. Yeah, I know it got smaller, but I wanted to pop it up higher on the screen. See if I can zoom that in for you guys at all. There we go. Using your calculator, normal CDF, because I want 300 or less, the normal CDF. Lower bound would be 0 students. Upper bound is 300 because we're stopping at 300. Those of you with Casios, your mean and standard deviation is switched around the other way. Those of you with the TI calculators, it's your mean and then your standard deviation. If you're much more comfortable with the table, you want to convert it to a z-score and look it up on the table. You do the value that you're interested in, x minus the mean divided by the standard deviation. That gives you your z-score, and then you look that up on the table. It came out to be exactly the same. Sometimes the calculator is a little bit more precise, but overall they're going to be very, very close together. Have you noticed though? I said that this was a really similar answer to this one up here. None of those digits are the same, but this is about what percent? About 1%, and this one down here is about 1%. So ballpark, we're in the same general playing field, about 1%. CDF instead of PDF? Or why did I use normal? Yeah. If it says binomial, you're going to use binomial CDF. Here they asked me to use a normal to approximate the binomial, and so I went ahead and did that. Normal approximations get used a lot, and so a lot of times we want to see, like, is this another one where I could use a normal distribution to get close enough? Absolutely. But there's a lot of software that will just automatically calculate the normal distribution, assuming that it's approximate. Okay, I want you guys to go ahead and flip in your packets to the very last page. It's going to be page 21. And I want you guys to spend the rest of the time today looking at something very similar to the Skittles activity. So use the Skittles activity to kind of help you work through this. You're welcome to work with partners. As a welcome back, we did Skittles before break. I do have Starburst right now to do your cherry Starburst activity. If for some reason you don't want any Starburst, please let me know as I come around. You're welcome to work in partners or small groups. It could be very, very, very similar to the Skittles activity that you did. And then we will debrief first thing tomorrow. Okay, just making sure I looked over and I didn't mean to go either one. That's okay.